Very good morning, dear students. In previous class, we have discussed the slope and deflection for cantilever beam. Slope and deflection calculation for cantilever beam carrying uniformly distributed load. I hope you have gone through the notes I have shared in the WhatsApp after studies class, and it is very quite simple. Just we have taken the moment about x-axis, x point, and at the distance of from the B, and later we have integrated from whole length from 0 to L. That is what we have done for slope, and for deflection we have considered the moment equation, and we have derived for 0 to L. And at the same time, if the deflection of the beam is asked and the slope and deflection of the beam is asked to calculate for half of the span carrying uniformly distributed load. So in previous class what we have considered is the uniformly distributed load is over the span, is on the complete span, but here it is only at A to C. But at the same time, if you observe here in previous class we have completed the considered the total length. The uniform distributed load is on the whole span, and that what we have calculated for slope and deflection. But they made the slope and deflection for the same span carrying uniformly distributed load only or half of the span, and remaining is empty. So in that case, how exactly the procedure gone, right? So in yesterday's class, we seen that the distance of x is considered from the B, and we have taken the moment, right? So here just the moment about A. See in this class, in this problem, what we had discussed the moment about the point X, right? So moment about point X we have considered because the span of the from the B, it is having the load which is UDL, but here it is not like that, it is empty. So here we cannot consider the moment at C because there is no any moment or load which is acting on the span of BC, right? So in that case, we can consider the moment at A, since it is an cantilever beam carrying UDL load. That we know that the load into the distance, the uniformly distributed load is converted to the point load. So the point load is considered at the center, and from that center we need the moment for the support at A. Just I would like to show that with an pen over. Okay, so this is the uniformly distributed load on this span. We have to consider this load to point load, that we need to convert it. So how do you convert it? So span into, that is load into span. So load is the W and span is L by 2, right? The load is W and the span is L by 2, then it is converted to point load over here, right? So after that we need to have the moment from part A point. So the distance from point this load to the distance of the point where we are exactly calculating the moment. So here the distance of this point to here, it is L by 2, half of the L by 2. So that is half of the span. The span is L by 2 here. It is nothing but what I have written, WL into L by 2. I hope you remember the for UDL load it is calculated by referring to W L into L by 2. That is the case we are using to calculate the moment for the spanning UDL load. That is what I have done. But instead of L, here it is L by 2. So after you solving, you will be able to calculate the WL square by 8. So this is the moment at A due to the UDL load for the L by 2 span is WL square by 8, right? If it is for complete span, it would be W, and that is WL by 2, right? In that case, it can be solved. But here it is quite different, having only half of the span. So once you draw the BMD diagram, that is bending moment diagram, if you draw for the given load, at A will be able to calculate WL square by 8 of moment, which is negative. However, we know that the clockwise direction in the cantilever beam is negative. And that is the only case we should remember here. The clockwise direction of cantilever beam is negative since the force is acting at this point, which is shown here, right? So after this, see, it is in parabolic form, it is not in a triangle, because since there is an UDL load, there should be an parabolic. If it is a point load, then it will be a straight line. Say it is like this. If the load is acting like this, if you draw an BMD diagram, BMD for the load, it will be like this, the span, and it is like this, it is straight line, right? So in if you, in the case if you having the UDL load on the span, it will be a parabolic line, and it is a basic concept we have already studied in the strength of material subject, but that should be carried out for the remaining subjects also, that is for higher studies. So in this case, the parabolic triangle will be having the CG distance of 3/4 of the span, 3/4 of the span, 3 by 4 times of L. So L is here L by 2. So L is here L by 2 because we have only for this triangle. So this is the length of the triangle, and this length is L by 2, right? So 3 by 4 into L by 2, right? So 3/4 of the L is the distance of CZ from this point. Why we are taking the CZ from this point is because we need to have the deflection like this. For that, we need to measure from the point where the deflection is maximum. Right? We cannot measure from here because here it is having a zero deflection at this point, and here we have the maximum deflection at this point. So for that reason, we need to measure the distance of CZ from C point, from here. And now this is the CZ distance from the C, and here we have WL square by 8 of the moment, that is the height of the triangle. So here just if you see, the area of this triangle can be calculated by referring to 1/3 of the base into height. So in the case if you have triangle, that is half base into height. So here for parabolic triangle, we need to carry, or we need to consider 1/3 of the base into height. So it is the base, it is the base having the length of L by 2, since it is base here, right? And it is height. So this is the height, which is WL square by 8, it is written, and 1/3 of base into height. So total will be WLQ by 48. Once you solve this one, WLQ by 48, this is the total area of this uh, parabolic triangle. So since we said, okay, so for moment theorem, so when you get an area of parabolic curve WLQ by 48, the moment area theorem need to be considered, because we need to have the slope. We need to consider the slope for this, since the slope is to be calculated by referring to the point where we are expecting. So theta b will be having a maximum that is slope compared to theta a. However, the theta a will be 0 because it is a fixed condition, will not be having any slope. It is holded, which will not allow to deflect, or which will not allow to get slope. So in that case, if you come from right to left, no, right to left over here from the cantilever, theta a can be considered, since theta a is 0, so theta b can be considered for the maximum slope here. So a maximum slope, for the maximum slope, what exactly the theorem we have studied in the theorem number 1. For theorem number what we have studied, that the moment area. So whatever the slope is calculated, that is considered for the M by EI diagram of the moment area. So moment area is WLQ by 48 EI, that is m by ei. M is nothing but the moment. So for that reason, WLQ by 48 into 1 by ei is to be considered. That is the Young's modulus of the beam as well as the moment of inertia for I. So that altogether WLQ by 48 EI, which is the theta that is the slope of B at the end uh, for the half span carrying uniformly distributed load. So this is the equation, this part, the theta A and theta B. So here if you consider, this equation is already we have studied, because however it is quite similar for all the cases. It is quite similar for all the cases, and theta b will be considered always m by ei. So m is here WLQ by 48, which is nothing but the area of parabolic curve. So which is WLQ by, that means area under the load is the m by ei diagram, right? Area, this is the area, this is the area under this load, under this load is m by ei diagram. That is what it is written here for theta b. So this is how you need to calculate the theta b value. At the similar case, the load value will be given, and the given value is considered in the calculation to get the maximum slope. So in coming time I will discuss those also. So here, next, the deflection. So the once the slope is calculated, the deflection is nothing but area into Cg. We all know that because we are dealing with the moment area theorem. Since this moment area theorem is gives the area into Cg. So here area we have already calculated as WLQ by 48 EI. So instead of this, we need to multiply the CG of the triangle. So CG is 3/4 of L by 2. So 3/4 of L by 2, just 3/4 of L by 2 we are referring, and just that will be a total of 7 WLQ L raised to 4 by 384 EI. So that is the total deflection. Once here the span L and the W load and EI value is substituted, then you will be able to calculate in mm, slope in mm, that this mm that depends on the load unit, the length unit, and EI units. If you are substituting the load unit in newtons and the length unit is mm, and E is Newton per mm square, I is mm cube. In this case, if you substitute the units, then you will be able to calculate the deflection at the end. So that means it is like this. So this distance is referred. This distance is referred for the as a deflection over here. So, however, and whatever I am discussing in the classes, those all are asked for the examinations only, because whatever I am referring, that is all question papers, and that is from question paper. I am referring for the clear understanding of concepts which they are going to concentrate on that. So now this is all about calculation of slope and deflection. So only thing is we have calculate the maximum moment for the load, and for that we draw an m by ei diagram. Once m by ei diagram is known, then the slope is calculated at the free end, and the deflection is calculated by referring to the Cg of the area under the load. So this is the basic what we have discussed. So now let us consider a problem. Let us consider a problem over here. The problem statement is like, so determine the slope and deflection at the free end of a cantilever beam shown below. So this is the cantilever beam having the span of 1.5 and 1 meter with two concentrated loads acting at one at end and another at point C. And for this, the EI value is given as 4000 kilonewton meter square. So 4000 kilonewton meter square is the EI value that is given. So for this, we need to have calculate the slope and deflection. So however, our first step is to calculate the bending moment. So for bending moment, here we have two loads. For two loads, we need to calculate the bending moment. So for point load in cantilever beam, to have the maximum bending moment at any point is the point load into distance. That is what here it is simple in cantilever beam, right? Previously, we have considered all problems with the uniformly distributed load. Here in this problem, we are considering the point load or concentrated load. So which is nothing but W into L for the point where we are measuring the moment. So if you are considering the bending moment due to this 10 kilonewton load at A, then 10 into this 1.5 will be 15, right? So 10.5, that is the moment at point A due to this 10 kilonewton load. Now for this 5 kilonewton load, what is the moment at C? So 5, that is the 5 kilonewton at the C, and this 5 kilonewton at A is 5 into the total distance. 1 plus 1.5 is 2.5, right? So 5 into 12.5, 5 into 2.5 will be 12.5 kilonewton of kilonewton meter of total moment is acting at the point A due to this load. So now this whatever we have calculated, that is demonstrated in the BMT diagram, which is nothing but we can say BMT. And however, whatever I am saying, it is we have already gone through this. If people have already gone through this, let us discuss once again. If you people have might be forgotten. See, for this, for the span of BC, if you consider the span of BC only. So in the span of BC, we have 5 into 1. We don't have any other load other than this 5. So for that, 5 into 1 will be the 5. That is the 5 kilonewton meter. So this is at C. Since it is the point load, you will be having a straight line. Will be having a straight line. So for this, the bending moment diagram will be in triangular shape for this span itself, because at the end we will be having another point 1.5 due to this 5 kilonewton load, and due to this 10 kilonewton load we have another moment. So at the A, the total bending moment will be 15 because of this 10 kilonewton, and because of 5 kilonewton it is 12. We are considering at A point. So for 5 kilonewton at A, it is acting 12.5 kilonewton meters, and 10 kilonewton is 15 kilonewton meter at the A. So 15 plus 12.5 will be 27.5. So in this we have 5 kilonewton load, which is considered over here. That means we are dividing the area to areas to calculate each other. That is each area, the total area we need to calculate by taking the triangular and rectangular portions. That means we are so once we know that the area and the distances of the bending moment diagram, the moment area theorem, that is nothing what we have considered for the discussion. And another one is conjugate theorem, that is another part. So in this moment area theorem, the slope is to be calculated. Then we need to have m by ei. So for m by ei, whenever the load is given, we know that for slope, the load, the area of bending moment diagram under the load, right? So area of bending moment diagram under the load, it is the line you should remember while calculating the slope of any of the member. Area of bending moment under the load, right? So that is the case we are referring for calculation of theta b. So theta b is m by ei. So from theorem number 1. So what is the theorem number 1? For theorem number 1, that gives or that defines the slope. So what we have discussed, that is slope theorem number 1, the change in slope between 2 points on a straight beam or straight member under a flexure. under a flexure, that means under a loading or bending, which is equal to the area of M by EI diagram between those two parts. That is what you must remember, and you must by head this point, or you must understood what is theorem number 1, which defines the slope. So that is what the theta b is equal to M by EI, it is written. So for theta b, area of bending moment diagram, area under bending moment diagram is just we have drawn the bending moment for the loads, right? So for these loads, what are the areas are there? That is what we need to consider, right? So now this is, I will consider 1, this is 2, and this is 3. However, you can consider any of the part as 1, 2, and 3. But here I have considered this part as the 1, this part as the 2, and this part as the 3. So part 1, and the dimension is 1 meter base, 1 meter for this base, 5 meter as a height, and which is triangle. So for that we can able to calculate that half base into height. Next, for 5, for this second section, 5 into 1.5 is the distance. So 5 into 1.5, which is area under load. The load, for the consideration of load, we have drawn this. Next, for third section, we have the triangle. So since half base is 1.5 meter and height is remaining of this rectangle, which is 22.5. right? So this is half base into height for triangle 1. So for rectangle, for section 2, length into breadth, it is 1.5 into 5, 1.5 into 5. And next, for third section, we have half base into height. Base is 1.5 and height is 22.5, which is triangle half base into height. So after all, if you calculate this, 26.87 is the total value of the total area. So for this, if you given EI is 4000, so given EI is 4000, that means just we are substituting here. So M is moment under minor bending moment area under the load is 26.87. This written negative is because it is cantilever beam, and which will be having the clockwise movement, and which is negative because we are drawing in negative side, negative point, or at downside. So now this 26.87 divided by 4000 will be 6.718 into 10 to the power 3 radians of the angle, because we are calculating the slope. We are calculating the slope, which is minus 6. Minus is because it is, which is downwards, which is in the below the axis, below the point, or below the beam, right? This is the radians. If you want to calculate this to degrees, you can calculate with 5 by 180, right? So now here for given loads we have calculated the theta b. So now we need to calculate the slope. So how do you calculate the slope? Just we need to have area into cg, area into cg for each of the part, what we have considered. So here it is simple, I have written. So before that, I hope it is clearly visible. Yes, you can draw like this. Okay, so for this, now we are going to calculate the area into cc. So this is the 2.5 distance, sorry, it is 1.5 distance, and this is 2 meter distance. Just on here it is, and here this diagram what I am drawing here. This is for 1 meter, and this is 5, and this is 22.5, right? So for this we need to have the bending moment, that is CG values. So here, just if you observe over the diagrams, it is 1.5 and it is 1. So since it is first one, half base into height. Whatever we are calculating, the deflection is for the point C or point end over here. This point, I think it is it is for B point. It is for B point. Here we are calculating. It is for B point. Here we are calculating the total slope. So that means whatever we are calculate the distance of CZ, that should be measured from this point, from the point B here. So now if you see the calculation, just it is written for section 1. Section 1 is 1 having half base as 1 meter and height as 5. It is height. So half base into height, and from the tip it is two-third of the base. So base is 1 meter, then it is two-third, 2 by 3, right? So this is the CG area into CG, or else you can write A into X bar, right? X bar is considered CG which is in X direction. So which is X plane, it is Y plane. In X plane we are measuring since it is X bar. So area is half base into height. From the tip it is two-thirds, since 1 by 2 into 1 into 5 into 2 by 3. So now uh, for second one we have 5 into 1.5, length into width 1.5, and for this the CG is acting at the center since it is rectangle. For this rectangle, if it is at the center, 1.5 by 2 is 0.75, but we need to measure the distance from B. So 0.75 plus this one will be 1.75 here. Here just see this is a rectangle part. For this rectangle part, 5 into 1.5, 5 into 1.5 is the area, and the CG, if you consider from the B it is still here it is 1, and from here it is 1.5 by 2, which is 0.75. So this is 0.75 plus this one. So altogether it is written as 1 plus 0.75, which is 1.75. So now it is completed for triangle 2. Now it is rectangle 2. Now it is for part 3. So in this part 3 again we have a triangular section, which is half base into height. So half base is 1.5 here, complete base is 1.5 distance, and now for height is 22.5, and two-third of the base, if you consider, so it is written it is 1, however we need to consider 1 over here. Now two-third into 1.5, two-third of the base, it is written 1.5, and altogether if we calculate it will be 1.667 for this span, and for this span it is 13.125, and now for complete of this one it is 13.33.75, like this. So once you calculate the value of all these, it will be minus is because again it is in clockwise direction, which is downward, because you cannot say it is clockwise since we are calculating deflection. If you are calculating slope, you can say clockwise. For deflection you could say downward. So now 48.54, and the EI value is given as 4000, so 0.012 meter, which is in meter, because we have substituted EI value is in meters, kilonewton meters. So if you convert that into mm, it will be 12.13 mm. That means what we have calculated is here, for the span of the beam of cantilever beam carrying two point load or concentrated load at a distance of 1 and 1.5 meter from the support of, it is 10 kilonewton and 5 kilonewton. If it is loaded, to 5 and 10 kilonewton, you are able to get the deflection of 12.13 mm at the end. This is what we have calculated. So that means which is downward direction since it is minus. So 12.13 mm because of these two loads with a distance of 1.5 and 1 for support A, right? So this is how the clear calculation is, and the slope and the angle for angle is calculated as 6.1718 radians. 718 into 10 to the power minus 3 radians. So, and this is how we people have to calculate the slope and deflection for given problem. And this on this discussion, I would like to give an assignment for you people over here. So whatever we have calculated for this, however, I will share these notes after this class. But I would like to to get the solution for the beam. You please consider this one as an assignment for you. It is a beam carrying uniformly distributed load on this span, not on this one. However, the remaining will be same L by 2, and this is L by 2. Okay, which is load and W per unit length, right? W per unit length. So now it is a support A, support C it is, and support B, right? So I hope it is clearly visible, Arun. Yes, Arun, it is visible. Vinay?
Yes, sir.
Vinay, it is visible. Monica?
Yes, sir. Visible, sir, clearly.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. It is visible, sir.
Okay, please take it as an assignment. However, we have solved this for this span carrying UDL load, but you people consider the load on this span and then you can draw it. You can have calculation for slope and deflection. Can you do this?
Yes, sir. You can do this.
Okay, right. Thank you. Okay, now and this is what we have discussed now. And again, in a similar case, if the I value is changed, if the I value is changed, and along with the uniformly distributed load, the point load is or concentrated load is acting in the span, then how exactly it would be, right? So in the particular span, if exactly the load is acting, that is in combination, here the load uniformly distributed load along with the point load which is acting. So since what would be the em by ei diagram and what would be the bmd diagram, like that. So here if you refer this question, it is asked to calculate the maximum slope and deflection for the cantilever beam shown below. It is quite simple. The question is just it is again we need to have the bending moment values for support A and support B. However, the bending moment at C will be 0. Bending moment at C will be 0, and bending moment at B is to be calculated, and the bending moment at A is to be calculated. So for this, I hope it is now it is clearly visible. So just it is observe. It is 12 kilonewton. It is 12. It is 12 kilonewton. Okay. So now it is 2 meter distance and it is 2 meter distance, and this 2 meter span having I value as 2i, and this 2 meter span having I value as I. This 1i. That means m by ei. If you consider here, it is I value is 2i. It is given, and here I value as 1. Now, if you calculate the bending moment at C, it is 0 because it is a cantilever beam. Now, bending moment at B, if you calculate, so this span need to be considered, right? So this span is to be considered. That means the span of BC carrying the uniformly distributed load of 12 kilonewton per meter length. So now for this, the simple formula is W L into L by 2. That is what it is written. W is 12, right? And L is 2 meter and L by 2. So L is 2 by 2 will be 1. So bending moment at B is 24 kilonewton meter. Now the bending moment at A, if you calculate, considering both concentrated load and UDL. So for bending moment at A, it is 12 into 4 because we have the total distance, because now we are calculating for point A. So total load is 12 for the span of 4, and since it is UTL, we need to consider the CG because the center of the load is to be considered. So half base into height, load, that is uh, 12 into 4 into 4 by 2, that is WL into L by 2. And apart from this, we have another load which is 24, which is 24 kilonewton concentrated load acting at the 2 meter distance from the A, which is 24 into 2. So total will be 144 kilonewton meters. So the maximum moment at A and maximum moment at B is 144 and 24 respectively. So for that, if you draw a BMD for this beam, will be like this: 144 at A, the total bending moment 144, and now this is in parabolic case because of the uniformly distributed load. Now it is suddenly it is having the point drop down point because of this vertical concentrated load. Again it is raised to 0 of having 0 bending moment at C, and it is bending moment at B is 24. Bending moment at B is 24. For this, if you draw M by EI diagram, for this, if you draw M by EI diagram, how it will be? Just see, observe here. At A, for A span we have 2I, correct? For A span we have 2I. So for this, so 144 is the total load or moment. So 144 by EI. So EI is E is similar, E is 1 and I is 2 times of I, right? So if you divide it 144 by 2 will be 72, by EI. That means just we are substituting the I value as 2, and that will be 144 by 2, right? Because M by EI we know, that, and M is here 144. So M is here 144, we have substituted, and I is 2I, right? I is 2I and E is as it is, right? So since it will be 72 by EI, we can write, correct? So now for B point, if you consider 24, since it is 24, this B point will be having 2I part as well as I part, since it will be carrying two parts. One is I part, another one is 2I part. So for this we can have 2 points over here. It will be have 2 points. So for 2I it will be again 24 by 2 into 12 by I, and for 1I it is again 24 by EI, right? So at this point it is C equal to 0 because we don't have any bending moment value at C. I hope it is clear for you people what is M by EI diagram here we have drawn. Now it is simple to calculate the slope. The slope is nothing but area under bending moment, correct? Area under bend, that is area of load, under load which we have considered. So what is the area? So here we have this M by EI diagram. For this M by EI diagram, here if you draw the line, that means to create the known shapes to calculate the area. So I just draw a line over here to separate this as a rectangle, this as a parabolic triangle, and another one, however, it is parabolic triangle. After all, we need to have the area. Area under bending moment will be the slope. So A1 is this. I will consider this as a one section. A1 is nothing but here I have written. Since it is 12, it is a 12 distance depth for the 2 meter. It will be 12 into 2, which is 24. Next, for 2, 1/3 of base into height. So 1/3 base is 2 meter. Base is 2 meter over here, and height is 72 minus this 12, because we need to have only this one. This 72 is complete for complete span, complete height it is, but we need only this much, because we are referring to the triangle having the base of this one. So for this, if you want to calculate the total 72 minus this height, if you deduct it, and remaining will be 60. 72 minus 12 will be 60. 60 is the base, and 2 meter is the height, you can say, and 1/3 of the total. So 1/3 of base into height, it is 40. And for A3 it is again same, 1/3 of base into height. 1/3 it is written. The base is 24. Base is 24 here it is, and height is 2 meter. Right. So it is 16. So 24 A1, A2 40, A3 16, altogether 80 by EI. 80 by EI, which is the slope. If the EI value is known, and we can substitute the EI value. Since here it is not mean that I, 2I and 1I, because however we have already considered the 2I and I value. Just we need to substitute the value of I. If the value of I is a 400, then it will be a 400. Here it is 2 times of 400, it will be 1 time of 400, like that. Just we are substituting the value of EI, then we will be able to calculate the exact value of slope for the given load. So now 80 by EI is the total clockwise direction, that means negative. The slope is in downward direction, that is in the clockwise direction, like this. It is in clockwise direction. So now to calculate deflection for this, what is exactly the procedure? Just we need to multiply the CG to this area. Each area, just we need to multiply the CG. It is quite simple to calculate the total deflection. For deflection at C, because at the free end we will be having the maximum deflection. That is what here we have done. However, in this calculation of slope, we have calculated the areas, correct? So just we need to have the CG values, right? Just we need to have CG values. So I will just discuss the CG value, how we have considered for this diagrams. So since we need to have CG from the distance A, from the distance C. First, at the rectangle we have 2 meter base, and it will be at the center, correct? And it is 1 meter, it is 2, and it is 1, because at the center it is for rectangle. 2 by 1, 2 by 2 will be 1. 1 plus 2 will be 3 meter of the CG for this rectangle from the C. So that means we need to multiply the area into CG for 24 into 3, right? So now for this parabolic triangle 2 will be having the CG of 3/4 of the base, right? Since it is parabolic shape, 3/4 of the base need to be considered. That is 3/4 of the base is 1.2. So 3/4 of the base is 1.2 means base is, right here I will write 3 by 4 of base. Base is 2 meter for this parabolic triangle. 3/4 of the base plus 1, and this is 2 meter, because we need to have the CG from this. And now the area of this is also same 3/4 of the base, but here we don't have to consider the distance of 2 because it is considered from the C itself. So that is 3/4 of the base. So it will be 1.5, I think, correct? So it is how we need to calculate for the complete CGs for each of the area. So once we consider the area of these, then just we have to consider the substitute the values and can able to calculate the value of that is deflection, which is 236.0 by EI. So if you substitute the value of EI, you can able to calculate the deflection with respect to substituted units. If you substitute the unit of L in meters, then you will be able to calculate the deflection in meters. That is how it is given. So in the similar case, this problem is also considered, right? And this problem is also considered. Next, you need to solve for this. Take a screenshot for this one and try to solve on your own. Whatever we just discussed, it is quite similar to this problem. Only thing is the unit load is acting at B in the previous problem, but in this problem the concentrated load is acting at a C, right? So I hope you people will try this. You people will try this, and once you get to know the simplification, you can able to contact. You can refer or you can cross check it, right? I hope whatever we have discussed today, it is clear for you. And if you have any doubts regarding the discussion, you can ask me. Else we can conclude this class. Okay, Chandrika, are you listening?
Yes, sir.
Yes. Do you have any doubts regarding the discussion? No problem. If you have, let me know that I can discuss. Else later on, you can take the screenshots and send me to the WhatsApp. Then I can give you the solution. And one more thing, whatever the classes are being discussed here is recorded and it is shared in YouTube. And the YouTube link is given to Mr. Vinay for A division and Mr. Arun in B division. It is given to you people, and please collect the link from them. And every day after the class, I have uploaded the videos with the concept what we have discussed as the title. And everyone, please go through that. And after the class, I have shared the notes. Please go through the notes and then verify the discussion and the notes, and then be clear with the concepts. Okay. Manjunath?
Yes, sir.
Yes, whatever we are discussing, it is clear for you,
Yes, sir.
right? Are you? Please, everyone, I would like to request you, please make one notebook and separate notebook for the subject, and try to discuss or try to write the class notes in that, and whatever the assignments is given and whatever the doubts is discussed, please go through that text notebook. Then you will be able to revise it at the once you got to know the concept. Okay. I hope the discussion is clear for you. After all, if you have doubts, you can contact me later on. Okay. Thank you for attending the class. Thank you.